Well, hello, ap2. It's time for the chapter 10, part 3, the next video. Woohoo, woohoo. Today's video, we're going to be covering a mathematical way of relating temperature and kinetic energy. So we want to be able to relate temperature and our kinetic energy. I started off a while back telling a story in class about the air in the room and how thermal equilibrium works, and that ended up with our things don't suck, they blow conversation. And in that conversation I said that temperature ultimately is related to kinetic energy, that when you talk about the temperature of a gas, for example, you're talking about the kinetic energy of the particles that make up that gas. Well, today we're actually going to relate those things together. Before we do that, we have to look at a couple of assumptions that we need to make. So, in your textbook on page 339, we can look at the 5 assumptions. Basically, these assumptions describe the fact that we're looking at an ideal gas, but just to go through them. The number of molecules in the gas has to be large. Well, we're going to say there are n molecules, capital N, and capital N needs to be large. Well, for our example, we're going to be looking at the air in the classroom, and well, there's going to be many Avogadro's numbers of particles. N is definitely large. The molecules will obey Newton's laws of motion, but as a whole, they will move randomly. So basically, this just means the particles have mass. By particles, we mean the air molecules, O2, N2, what have you. The particles have mass, and they will fly around obeying Newton's laws. Okay? Randomly means that there's no preferred direction. That means no one direction of velocity is preferred over any other. Particles, basically all n of them, cover basically all possible arrangements of velocity. The molecules interact only through short-range forces during elastic collisions. What we're saying is a molecule in one corner of the room is not exerting a gravitational force on a molecule in the exact opposite corner of the room. Now, we know this is just an assumption. There really are long-range forces, but we're assuming for simplicity that we are not dealing with long-range forces. The molecules make elastic collisions with the walls. Elastic collisions, to remind you, means that there is no exchange of energy, so the kinetic energy is conserved before and after the collision, and as always, momentum is conserved during the collision. This is important because we're going to be describing molecules banging into the walls, exerting forces. All the molecules in the gas are identical, so I know the air in the room is made of oxygen 2 and nitrogen 2 and some carbon dioxide, and God help us, carbon monoxide, but we're assuming that the gas is an idealized gas, so all the particles, all the molecules, atoms, whatever we're looking at are going to be identical. Okay, so there's our assumptions, an ideal gas. So we want to now relate temperature and kinetic energy. And what we're going to do is we're going to consider a particle, a group of n particles, capital N particles, flying around a room like our classroom. For simplicity, we're going to assume the classroom is a cube. So our classroom is going to be some cube, and each side of the cube is going to be length d. So we got a d by d by d cube, and there are n particles inside, and each particle has a mass m, and the volume d cubed would be v. Okay? So what we're going to do is we're going to look at the x component of one of the particle's velocities. So we're going to look at one particle, and we're going to look at the x component of that particle's velocity. So we're going to be looking at just the x component. Now obviously particles are traveling in 3 dimensions, so the velocity is going to be a vector made out of an x, a y, and a z component. And if you remember from last year when we did our 2-dimensional kinematics, we remembered that when you push a cart off the table, we can treat the x part of the velocity and the y part of the velocity, the x motion and the y motion, we could treat completely separately. So we're not playing any special games here, we're just doing something that we're allowed mathematically, and that is to treat just the x component of the velocity. So when we start talking about Vx, remember we don't mean to say that the particle only moves in the x direction, we're just looking at the x component of its motion, okay? So one particle, its x component. So what we're going to do is we're going to imagine that we have our standard positive direction that way and our standard negative direction that way. And we're going to say we have one of the walls of the container there, and we're going to have some particle, and it's going to be traveling that way with some velocity, in this example, negative Vx. So the x component is negative. It's traveling towards the negative direction. Okay? That particle is going to hit the wall, and after hitting the wall, it's going to bounce back that way with some positive V sub x. And what we're going to do is look at the change in momentum. Okay? So let's do that. When the particle travels, and it's going to experience when it hits the wall some change in momentum. So we're going to look at the change in momentum, again just the x component. Change in anything is going to be the final momentum minus the initial momentum, so final minus initial. And that change in momentum will be the mass of the particle times the velocity minus, and the initial velocity, which was in the negative direction, V sub x. And that gives us a total change in momentum in the x direction of 2 mv sub x. Okay, so we continue. Now that we know the momentum, we can actually relate this to the amount of force that particle exerts on that wall as a result of that collision. So the force that particle exerts on the wall is going to equal the change in momentum over time. Now some of you might not remember where that came from, so let's go to the Wayback Machine. Force equals ma. Acceleration is change in velocity over time. Well, m times delta v, that's just what we mean by change in momentum. So the force would equal change in momentum over time. Hey, look, that's what I said. Cool. So we have that force is change in momentum over time. Well, the change in momentum was 2 mv sub x, and that's going to be over time. Cool. Well, time. How much time does it take between collisions? So if we, and I'm going to scroll back here so I can illustrate this. If we envision a particle traveling this way, hits the wall, exerts some force on that wall, we're calling it F1, and experiences a change in momentum, now that particle is going to go this way. And it's going to go this way till it hits the wall over here, and then it's going to come all the way back, and then it's going to collide with the same wall. So we're going to have a force, and then a force, and then a force. So the distance between collisions is going to be twice the size of the box, right? From here to the next wall is going to be d. So if it's going to collide, it's going to travel a distance d, and then another distance d before it collides again. So the distance is going to be 2d. Why do I make that point? Well, because if velocity is just going to be distance over time, and our distance is 2d, then our time can be written as 2d over v. In this example, v is going to be the x component, so I should say x component for that. So I can substitute this time in here, and when I do that, I will come up with that force is going to equal mv squared over d, right? Vx, so we're dividing by t, so Vx goes up on top, so we get squared. 2d goes on the bottom, that 2 and that 2 cancel, and we end up with this expression. So that now gives us the force being exerted by the particles, by one particle on one wall. Now, in only the x direction. So we're well aware of the fact that there are not just one particle, there's actually n particles. So the force in just the x direction by all of those particles would actually be v1x squared plus v2x squared plus vmx squared. Or I'm going to try to write that n again. Oh, I just messed up the whole thing. Let's try that again. Plus vmx squared. So that's all n particles, and they all have the same mass, and they're all traveling the same distance, so that gives us the total amount of force. right? Now, this term right here, if I were to take that term right there and actually divide it by n, in other words, if I were to take v1 x squared plus v2 x squared plus vn x squared, if I were to take that and divide all of it by the total number of particles, then by definition what I've determined is the average vx squared, right? If I take the total, if I take all of the values, add them up, and divide by the total number, I get literally the average of all those values, right? Does that make sense? I just asked you a question and you didn't answer. Well, silly me, I'm on video. Duh. Anyways, that term we can then say is equal to the average times this. So I can take that and substitute the average v squared and n. So I would get that the force would actually equal m over d times n times the average, not vector, average v squared. So that gives me now the force of all of the particles looking in just one dimension. So that is the total force on one of our walls by all the particles in just one dimension, in this case the x dimension. Well, we've got all the particles taken care of now, but we are looking at only one dimension. We need to look at this three-dimensionally. Well, I'm not going to explain this next piece much more than to just say the word Pythagoras, and to point out that in Pythagoras that this equals this in vector language plus this plus this. So that vector is made of an x, y, and z component. And if I were to do this, and this is the part I'm not planning on explaining. Hopefully you can see, hopefully you see it. And if I were to take the average of each of those, I would end up with that. Now, so the total average square velocity is going to be equal to the average x squared plus the average y component squared plus the average z component squared. Now, one of the assumptions we made before was that we're moving totally randomly. Totally randomly means there's no preferred direction, which means that the average velocity, I keep writing vectors for that the average velocity in the x direction, we're talking about squared, is going to equal the average in the y direction, is going to equal the average in the z direction. There's no preferred direction, so there's no more of them doing x than doing y than doing z, so all those components on average would work out the same, because there is no preferred direction. We're moving totally randomly. And if we do that, that means then that that average is going to equal 3 times that average, right? If all those are equal and I have 3 of them added together, then the average is going to be 3 of those, right? Which means I can substitute that as being 1/3 the total average. So I can make that nice substitution. And where am I going to make that substitution? Why, right there. So let's do that. So now we have that force is going to be equal to n over 3 m over d v squared. Double check that I did that right. N over d m. So we have n over 3 m over d, and then that becomes this. Yep, we did that right. So we got. So now we have our force in 3 dimensions. Well, we can relate that to pressure because we know that pressure is force per area. So that means that our pressure is going to be the area, which is going to be 1 over d squared. 1 over area is 1 over d squared. And we are now going to have another 1 over d, we're going to have an N, an M, and a V squared. So that gives us our force, all this stuff. That's our areas right here. So that's all of this is our force, N over 3 mdv squared. Oh, I'm missing a 3. I'm glad I went back and reviewed that. There's my 3. Okay. So now we got it all. Well, d squared and d, that's just going to be 1 over d cubed. 1 over d cubed is just the same as 1 over volume. So this should turn into, if I'm thinking of this right, 1 over the volume, that's that, n over 3, and then mv squared. Man, if you guys remember kinetic energy, mv squared is, we're getting really, really close to kinetic energy here. Ooh, this pleases. So, kinetic energy, to remind you, is 1/2 mv squared. So, mv squared, so mv squared should equal 2 times the kinetic energy. And let's do what we always do and substitute. So that means that pressure is going to be 2 kinetic energies. So I'm going to have 2 kinetic energies, and I'm over my 3. I'm going to have N over V, and there's my average kinetic energy. Why is it average kinetic energy? Well, remember, this is in terms of average velocity here, average velocity there. So if I'm substituting in, that gives me average velocity means average kinetic energy. And this equation can also be written then as P equals 2/3 N over V times 1/2 mv squared. Just to remind you that average kinetic energy is that, okay? And we had 2 of them, which is where this all comes in, okay? Alright, so we now have a relationship between kinetic energy and pressure. Well, we know that there's a way to relate pressure and volume, so, and pressure and temperature. So we should be able to bring temperature into the mix here pretty easily by simply remembering that PV equals NKT, and that means that if we take this equation and move this V over here, we would have NKT should equal 2/3 N times this potential energy here. So I should be able to say that NKT should equal 2/3, remember the V moves over, N times our average kinetic energy. Okay, so all I've done is I've taken this V, multiplied it by that V, so now I have PV equals all this, and PV equals all this. So now I relate this and all this together. Alright. Well, once we've done that, we see that that can cancel. And then I can say that 3/2 KT is equal to 1/2 M average V squared. So I can say that the average kinetic energy, I'll just write it here. So I can say that the average kinetic energy is equal to 3/2 KT. What if I want to know the total kinetic energy? Well, maybe this will make sense. The total kinetic energy should equal the number of particles times the average. Right? If the average is just add them all up and get the total and divide by n, then if I multiply the average by n, I should get the total. So if the average kinetic energy is this, if I multiply this by n, I should get the total kinetic energy. So I should be able to say that the total kinetic energy is 3/2 N KT, which, if you like the other way better, that's also the same as 3/2 little n RT. And that gives us the total kinetic energy. Well, that total kinetic energy is the kinetic energy of all of the particles that make up our gas. That total kinetic energy that makes up our gas, we call that the internal energy. We call that the internal energy. We call it the internal energy because it is the kinetic energy of all the particles that is internal to the object. It's subatomic, it's atomic, it's molecular, it's not macroscopic, it's in the inside, right? So we give the symbol of capital U for internal energy, and the internal energy is 3/2 nkt, or 3/2, I shouldn't have tried to write it there, or 3/2 nRT, depending on which way you like it. Alright, so there we have it. We've now related kinetic energy and temperature mathematically, and we've also referred to the kinetic energy of all of the atoms that make up a thing as that thing's internal energy. So when I supply heat to something and its temperature changes, what I'm really doing is, via collisions, changing the kinetic energy of all the particles, which is really just a mathematical derivation of that story I told about thermal equilibrium, in a way. So, hope that makes sense, and